the lowest energy here. That lowest energy, there's a name for it because it's important. That when n is 1, that energy level, so E1, is just called the ground state energy, meaning the lowest, sort of like the ground floor, the lowest level. Right? So the ground state energy when n here is 1. Okay, so that means the uncertainty in your energy is more or less the ground state energy, and that follows from the Heisenberg uncertainty principle. So if you had the energy n equals 0 here, you'd get the Heisenberg uncertainty principle contradicted, right? And that would be a big no-no. Okay? Right, a couple of other remarks. I haven't written it down, but we'll probably do it a bit later. But there's something in quantum mechanics called the Correspondence Principle. And the basic idea is when you take quantum mechanical predictions and you extrapolate them to high numbers, like when your parameters have numbers and you let those numbers take high values, you tend to get the classical conditions, what classical mechanics predicts. So there needs to be a kind of correspondence between the predictions of quantum mechanics and the predictions of classical mechanics. And that tends to happen, for example, when you let Planck's constant go to 0, or you let n, for example, here become a very large number. In that case, the difference between the energy levels tends to smooth out, and like, for example, if Planck's constant, if that goes to 0, then the difference between these energy levels goes to 0, right? So you lose your quantization. Everything becomes smooth. Energy values change smoothly. That's an example of the correspondence principle. We'll probably come across that again a bit further into the course. All right. Now look, now here's a sort of an example. As A here, so this size, as it increases, so as A increases, these energy levels go down, right? As A gets very large, the difference between these energy levels, say En plus 1 and En, that difference gets smaller and smaller until it's effectively just a continuum. It's just the energy can take on any value, as in classical mechanics, right? So you get this sort of thing. All right. Now the next thing. So we've solved now the energy, the discrete values of the energy, quantized energy for this case, the infinite square well potential. Now let's actually solve for the wave function, the u itself. Okay. Well, we know we've got a form here. We've got a value here for u. A sine plus b cos, right? So we've got that. Now remember, now we can impose the normalization condition. That's one of the constraints. Normalizable. Remember, you integrate the square, and that over the whole volume or the space you're talking about, that needs to be 1, right? Well, u is 0 outside the A region, right? So so this integral here, so we square the u by dx, integrating it over the region minus A to A, that must be equal to 1, right? The electron, the particle, whatever, must be in this region here somewhere, right? So the probability of finding it in that region somewhere is 1. It's certain, in other words. Okay. Now let's say for even n, when n is even, so his n is even here, and which case are we talking about? This case here, I think. There's this case. So B is 0, right? B is 0. So the A is non-zero. So we're going to use this condition to give us a solution to A. Now, what's big A? What is this A here? Right? So when B is 0, this drops away, and you're just left with big A sine alpha x. Okay. So plug that in and square it. So you'll get a squared sine squared alpha x. Okay. Okay, so here, right? There's your alpha x. There's your alpha. There's your alpha, right? X. Do the math, do the calculus, and you'll end up. Now, all this has to be equal to 1, right? This, which is just this, has to equal 1. The probability is certain that you'll find a particle somewhere in that region. Okay, so therefore a squared is 1 over a. Big A squared is 1 over a. Now, now you can do a similar thing. Okay, so this this is for n is even. All right, so so we now b squared is the same. B squared, similar logic, is also 1 over little a. All right, so for n is even, when n is even, b is nothing. So we now know that big A here is now 1 over square root of little a, and so we have now a solution. We now know what u is. Okay, so for n, when n is 1 here, we can plug that in here, and we'll get this is what u1 squared looks like. Right? There's your probability density. So on this axis you've got u1 squared. Now why 1? Well, the 1 just corresponds to the ground state energy when n is 1. Okay? And that's what your u squared, because probability density looks like. It looks like this, sort of symmetric about the origin. All right. Now for u2, so that's when n is 2. That was the n. That's the n is even case, and this is when in the n's odd, u will be of this form. Yeah, they're similar. So that was the odd case, actually, when it's the ground state energy when n is 1. So your u squared will look like this. And when you're taking the next higher energy level up, so u2, so your n is now 2, so you're talking about e2, the second discrete form value of the energy. Okay. So you square this, and you'll get something. This looks like the humps of a camel. Again, symmetric about the origin. Okay. So so in other words, the probability of finding the particle gets very low near the edges. Right. That's predicted here. For the odd energy case, the highest probability is finding the particle in the middle, around the origin. You know, in this region, whereas if it's if the energy is odd, 1, 3, 5, whatever, there's 0 probability of finding the particle in the middle, right? That tends to peak, sort of, half, in the middle of of either wing, the left side or the right side. Okay, and again, you got this kind of symmetry, right? So summarising. For this particular case, our first, and we'll do quite a few of this kind, we impose these constraints, we solve the time-independent Schrödinger equation, we're given, usually given the potential for the problem. So in this case, we know that it's 0 in this region and infinite outside it. So we solve the time-independent Schrödinger equation, we get, using these constraints here, these conditions imposed on the wave function, and we get discrete values of the energy. Very interesting, right? Quantum mechanics, quantized energy. And then in the last step here, we can actually solve for the wave function, in this case u, right? And once we know u, we can find the probability densities that you integrate over to get the actual probability of finding a particle in a given region, given volume. Right? So here is the case for U1, the ground state energy. So when n is 1, here, right? It's sort of looks like how would you describe it? Like half an ellipse or something, right? Symmetric. and again it's symmetric, but this time like two humps of a camel, and that's in the even case for the even energies when n is 2. And you could when you can do it for n is 3 and 5 and 4 and 6 and so on. Okay, so we've done our first solution to a time-independent Schrödinger equation, and our first high-definition session. So curious to see how this works out.